Welcome to the first day of e-learning in Calc BC. I'm sure you're all very excited, as I am. We are starting today with 10.1 polar coordinates. Should be pretty quick. It's pretty simple. Some of this you will have done last year. We'll add a little bit today, and then certainly as we move along, there'll be some new items, but a lot of this hopefully will be a review for most of us. Polar coordinates based off the idea that instead of graphing an x comma y, so kind of out with that, your points are going to look the same, but they mean two different ideas. Instead of x here, y here, this is your r, this is your theta. This tells us if we're going to be graphing something, we want to first identify what angle we're going to be looking at. So if you're standing here and you're told to graph this point at the top, 2 comma pi, what that really means is we want to look in this direction towards angle pi. And then in that direction, we want to take 2 steps in that direction. So if this is us, we'd be looking at pi and go out towards that angle 2 full steps. So here's 1, here's 2, that's going to be this point. That's 2 comma pi. All right, so we start at the origin, turn at whatever angle I'm telling you to look at, and then go out that number of units. That's where you're going to plot your point. So pretty simple. First 4, just a little practice, making sure that we understood that. If I ask you to plot point A, that's your R, that's how many steps you will take. Pi over 4 is the angle at which you will take those steps. So we would obviously know this is pi over 4. We're going to go out to the 1, 2, 3, 4th circle, our 4th radius. That's going to be the point A. All right. So, oops. So there's A. If I ask you to plot point B, that means you're going to look at 5 pi over 4. So here's angle 5 pi over 4. That's the direction we turned and look at. If I tell you that you have a negative r, what that means is instead of going out in that direction, 1, 2, 3, and 4, we still look in this direction, but the negative r tells us we actually want to go backwards from the angle that we would have been looking at. So we look in that direction of 5 pi over 4. Oops. But you're going to go backwards 4 steps. So instead of going in the direction, we go backwards 1, 2, 3, 4, and what you would then find is A and B are actually the same point. So you'll see there's a couple different ways we can identify the same exact point. If we did C, you're going to look at negative pi over 2, so we can do a negative angle, just like we would normally with the unit circle. This would be a negative pi over 2 down here. Positive r means we are looking in this direction, and we would go out 2 steps. So this is point C. 3 pi over 2. So if this is, again, angle 0, if we go around our circle to 3 pi over 2, that would also be this point down here. And from that, looking at that point, you're going to go out 2 steps. So we look at 3 pi over 2, go down 2 steps, and you'll see C and D are the same point as well. So with a negative angle, with negative r's, there's multiple ways that we can plot some points. But more than anything, just understand that this is always r, comma theta, and then that's how we would graph. That's plotting simple points. Just to kind of illustrate, there's different ways that we can label the same exact point. When I ask you to find all polar coordinates of each point, one of the things that we could do for this one is go out to 3, and then pi over 4 is basically the same point. But another thing we could do, I didn't show up at the top, is we can continue to go around that circle. So if I go pi over 4, add 2 pi, go out to 3, it's the same point. I could go 4 pi, 6 pi. Every time I turn 360 degrees, I'm going to end right back where I started. So we would write that as 2 pi times n, just to indicate that we can continue to go around our circle 2 pi and continue to end up at that exact same point. We could also possibly use negative 3 if we wanted to say, let's look at 5 pi over 4. So you're looking at 5 pi over 4, but you go backwards. And then just say plus 2 pi again, over and over and over and over again. 6, negative 3, and then say pi over 4 plus 2 pi n. Or we could say positive 3 but we would be looking at 5 pi over 4 plus 2 pi n. All right. So pretty simple. Let me make sure that's right as I do this real quick. 5 over 4, 5 pi over 4. Yeah. All right. Those are your points. Next set of problems is just going to be, instead of just a simple point, what if we have an equation? What if we have an inequality? Still based off the idea that r is your radius, theta is your domain. So if we look at number 1 here, all you're going to see is your r equals 2. So what that means is no matter what angle we're looking at around our graph, around basically what's the unit circle, you're always going to have a radius of 2. So if I look at angle 0, my radius is 2. Pi over 6, my radius is 2. And here, every single one of these has an r of 2. Well, those are the angles we know, but would also include all the angles in between, so that what would ultimately develop is a circle with a radius of 2. So with 2, r equaling 5, that means no matter what angle we look at, our radius is always going to be a 5. So my graph wasn't quite big enough. So we would extend this out. We have a circle around the circle of the 5th radius. 3, this will tell us to look at pi over 6. So here is pi over 6. And then we would want every radius that is equal to 0. So here, every radius that is greater than 0 towards pi over 6. So 1, 2, 3, 4, 5, 6, forever and ever and ever. But also 1.5, 2.5, 3.5, 1.6, so on and so forth. So that what we ultimately end up with is what we would call a ray. Starting at 0, looking at pi over 6, and we would want every radius towards that angle pi over 6. When we graph all those together, you end up with what would be a ray. Or similar, you're going to be looking at pi over 6, but just to make sure we understand the whole negative r, we're looking in this direction, but since our r is a negative or 0, we would want r of 0. And then we could go 1 step backwards, 2 steps backwards, 3 steps backwards, 4 steps backwards. That's why it's negative. So we're not going in this direction at all. Gosh. Let me get rid of those points. And then we would want all the r's in between as well, so that we get another ray, but now we're actually going towards 7 pi over 6, because that's the negative r for pi over 6. 5, between angle 0 and pi over 2, so we would want pretty much any angle in between here, so anywhere from 0 to pi over 2. Why that pops up? Within those 90 degrees, we would want every r of 1, so we'd have a little circle here, and an r of 2. But since it's in between 1 and 2, we would also want the radius of 1.1, 1.2, 1.3, 1.5, which when we do all of those would basically result in what would be kind of a quarter of a donut or a quarter of a washer between angle 0 and pi over 2. 6, if we're looking at angle pi over 4 here, we want every radius up until 2, so that would be 2, 1, 1.5, so that would look like this. But we would also want every r up to a negative 3, so negative 1, negative 2, negative 3, all the r's in between, so that if we're looking at pi over 4, hopefully you can draw that straighter than I can with this pen, we ultimately end up with a line segment looking at pi over 4, going 2 steps in the positive direction, as well as every step in the between, going 3 steps in the negative direction or opposite direction, as well as every step in between, so that we end up with a line segment. 7 is an interesting one. There are no angles, so that means for every single angle, we would want an r equal to 1. So that's our circle around this first one. But we would also want a circle at 2, and then 3, 4. But similar to some previous ones, we would also want one around 1.1, 1.5, 1.6, so that pretty much, if we want every r greater than or equal to 1, we basically end up with, and this would just get shaded forever and ever and ever and ever and ever, something that would look like this. Basically, we just have a hole in the middle. Everything outside of that hole is going to be shaded. All right. 8. Excuse me. Between negative pi over 2 through positive pi over 2, we would want every radius from 1. So that would give us a half circle here up until 2. So another half circle around 2. But since it's an inequality, everything in between 1 and 2, we would end up ultimately getting this shaded if we filled in every radius between 1 and 2. So we would end up with what is ultimately kind of half a donut or half of a washer. Last one, looking at 0 to pi over 6. And we would want every angle in between there. And then towards 0, we would want an r of 0 of 1, 2, 3, 4, as well as everything in between. So we have a ray towards 0. Towards the angle pi over 6, same thing. We would want r equals 1, 2, 3, as well as everything in between. So we'd have a ray there. But also within those angles, so every angle in between, we would also have rays everywhere. So we would have a ray halfway through, just above it, and above it, so that if all of these were drawn in between pi over 6, you get kind of this infinite piece of pi. So those are our equations and inequalities, and again, not terribly difficult, but all of those you would need to be able to do come like a quiz or a test time. Last thing for the day is how can we convert polar coordinates into Cartesian? So polar again is r comma theta. How could we turn that into something like x comma y, or vice versa? Could I take x comma y and turn that into r commas and thetas? So we want to be able to work back and forth. The conversions are based off of this as a circular measure. If we put a dot in the middle, so do that. Draw out an x-axis. Draw vertically a y-axis. So here's x, here's our y. And then draw out a ray so that we hit our circle. This is then the radius of the circle. So label that r. We would drop down an altitude to the x-axis here. So form a 90-degree angle. And then this point, since we're centered at 0, 0, this point, this would be your x-coordinate, whatever the horizontal change is, and whatever this guy is, your y-coordinate, would just be the vertical change. So kind of unit circle stuff, we have this angle here. If we just kind of go through some trig stuff, right triangle trig, SOHCAHTOA, Pythagorean theorem, we come up with what are ultimately these conversions down here. If you look at this angle, if we talk about the cosine of that angle, if we look at this angle, the cosine would be the adjacent side of x over your hypotenuse of r. Solve that for x. And what you would get is x is equal to r cosine of theta. So if we could look, we want r's and thetas to become x's and y's, or x's and y's become r's and thetas. If we look at our two sides of this equation, on the left side is r's and thetas, on the right side is our x's and our y's. So that's one way that we're going to be able to convert that x is always equal to an r cosine theta. Second one, if we did sine of theta, the opposite of that angle would be r. And then the hypotenuse, the opposite of that angle is y. The hypotenuse would be r. We can solve that for y. So that y would be r sine of theta. That's our second conversion down here. We have x's and y's on the right, r's and thetas on the left. That's one of our conversions. Third conversion, you can see there is nothing more than the Pythagorean theorem. You have a right triangle where here's your x, here's your y, there's your r. So we can just say x squared plus y squared is equal to r squared. We haven't really thought about this in polar before, but if you notice, you have x's and y's on the left, r's and thetas, in this case just an r on the right. So that is a conversion we can use to go back and forth. And then last but not least, if you did the tangent of that angle, you'll see that the opposite side is y, the adjacent side is x. You have thetas on the left, you have x's and y's on the right. That's a conversion. So those four here, you'll want to know pretty well. Those will definitely be things that you'll see often. So then the last thing is, let's go ahead and do some of these conversions. Rewrite the following polar. So if we were to look at all 6 of these problems, they're all r's and thetas. We want to write them as Cartesian, which basically means x's and y's. I then ask you to state what the graph would result in once we've done that conversion. So for number 1, this is a direct substitution. If you look at the top here, r cosine of theta is x. So that would be x equals 2. When I ask you what that graph would look like, this would be a vertical line. All right, through the x value of 2. 2, if we rewrote this just a little bit, this is really our cosine of theta times our sine of theta, equaling a 4. Our cosine of theta is x. We're multiplying that by our sine of theta, which is y, equals a 4. If we solve that for y, you get y equals 4 over x. No specific name for that. It would have a vertical asymptote at 0, and it would look like this, if we were to kind of sketch out what that graph looks like. 3 is pretty simple. R sine of theta is one of our conversions at the top. R sine of theta is directly equivalent to y. So in this case, y would equal 3. And then obviously that would have to be a horizontal line through the y value of 3. Or our cosine is x, our sine is y. Since this is r squared cosine squared, this is just x squared. R squared sine squared would be y squared equals a 1. This is something we haven't really talked about. You would have done it a little bit last year in Math 3. If this was a plus sign here, it would be a circle. Sometimes it's an ellipse if our denominator has different values. If there was a minus sign, what this was a good old-fashioned hyperbola. All right, so we'll have to remember those a little bit. 5 right-hand side is pretty simple. 1 plus 2x. Our cosine theta is 2x, or is x. So we have 2 times x. The r, if we look at the top here, we would want to probably use this conversion. X squared plus y squared equals r squared, which means r would have to equal plus or minus x squared plus y squared. So that's what we plug in down here. X squared plus y squared, positive or negative. That's a plus minus sign. If I square both of those sides, we would get x squared plus y squared equals 1 plus 4x plus 4x squared. Wait a minute before you get all that. And then we have to identify what is that graph. So this is a 4. So what I'm going to do is I'm going to move these over. So I'm going to subtract x squared, subtract y squared. So we have 0 equals 1 plus 4x plus 3x squared minus y squared. Now, last year you probably would have done a lot of completing the square, figuring out sort of major axis, minor axis, all that good stuff. But once we can see our square terms here, in here, and the fact that we have a difference of those, or one of those is a negative, that would be very similar then to number 4, where we had our square terms and we were subtracting those. Just like number 4 would have been a hyperbola, since we have square terms with one of them negative this would also have to be a hyperbola. You would not really be responsible for having to complete the square. All that good stuff that you would have done last year was a little more than what we need to get into for this. Then, last but not least, number 6, what we would just want to do pretty much to create some r's and sines together is take this denominator and multiply it over to the other side. So you'd have r times the sine theta minus 2 cosine of theta equaling 5. So then you'd have r sine theta minus 2r cosine theta equals 5. Once that's done, and it's pretty obvious, hopefully, r sine of theta is y minus 2, and then r cosine of theta is x. That would equal 5. And what we then end up with is a pretty simple little line, y-intercept of 5, slope of 2. So, thank you for letting me entertain you for 22 minutes. I hope e-learning was as exciting and scintillating as you had hoped it to be. You have the chapter schedule hopefully in your possession. If you wanted to look through the book, try some of those problems, feel free. But that's day 1. We have 3 days. Hit those the next couple of days, and then see where we're at for next week. All right. Hope you enjoyed that. We'll talk to everybody later. Bye.